Okay, let's go ahead and get started. Imagine you have something that's worrying you if you're out here on a Thursday night. What might it be? What questions can I answer for you? Okay, let's go home. Yes, sir.
Can we ask like specific questions like pertaining to a problem?
Yeah. Yeah. I think we had a question over here while you're looking for yours.
When we need to worry about when the charge is the test charge,
When do we,
test charge, if it's electron or proton, when we need to consider that into how it's going through near plates. Because sometimes it doesn't matter what the charge is, and other times it does affect its movement.
oh, no, it always matters. It's just when I'm setting up an electric field, I don't care what the test charge is, because the test charge doesn't push on itself. But when I'm looking for the force on the test charge, then it matters drastically what it is, whether it's an electron or a proton. Because if I have an electric field that's, let's say I've got some source charge. If that's a positive source charge, it's going to set up an electric field that's always away from it. And so let's say that right there, the electric field, I'm making this up, was 16. And that means that if I was the same distance over here, it would be, again, 16 newtons per coulomb, regardless of what my test charge is. But if I put a test charge, and that should be away, I just don't draw very well. Okay, if I put a test charge of, let's say, plus 2 coulombs here, then I'm going to get a force that's 32 newtons. But if I put a charge that's minus 2 coulombs, I'm going to get a force this way that's 32 newtons, the opposite direction. And that's from this vector equation that if I take the electric field and multiply it by my test charge, this is my rate, this is my price of a gallon of gas, and then I multiply by how many gallons I want, and that's going to give me what I really care about, which is the electric force on that test charge. And so you see that if this is to the right and this is negative, that's going to be to the left. But if this is positive, these will be in the same direction. Your question, sir, you found it?
Yeah. To be honest, I understand it now, but could you go over real quick on the partial charges again? I just see how the partial charges.
Yeah, so when we spread out the charge over a region, we found that we didn't have a formula for finding the electric field due to that kind of charge. And if that was a total charge of capital Q, call it Q source, and we wanted to find the field at some location out here, since we didn't have a formula for an extended charge like that, what we do as a gimmick is we break that charge up into a number of point charges, because we know how to deal with a point charge. And since I've broken it up into 9 chunks, each of these chunks would have Q sub S over 9. Now, spreading out the charge like that reduces its effectiveness in creating an electric field. And that's because if I look at the contribution due to this charge, it's away from the positive. And we'll call this chunk 1, and we'll call this chunk 9. Well, chunk 9 is going to give me a contribution away from the positive. And by symmetry, these contributions are going to be the same size. And you see that part of that adds and part of it cancels. This is going to cancel with that. And it's only this part that's going to survive. And so because of that cancellation, it's always going to be more effective to put all of your eggs in the same basket. And if I had the same charge here, and it was, let's say this was a distance S and this was a distance S, this would give me a much bigger force, or field, I should say, than this, because they're all pushing in the same direction.
So when would I know when to split up that big charge into smaller charges, or treat it as plate charging? Will that be?
Well, anything that's a plate, you've got a formula for. Anything that's not a plate is either a point, or else you gotta represent it by a bunch of points.
So if you give us a curved charge.
Then you gotta break it up into chunks. Yeah, gotta break it up into chunks. Other questions? Nothing? You got nothing? Yes, Stephen.
Go over three.
This Stephen.
3B on tutorial 3.
3B on tutorial. Oh, okay. I keep forgetting that question 1 is, did you watch the movie?
Yeah, me too.
So 3B. So. Okay, so 3A acts, is there an electric field inside the metal? And that's no, there never is. What charge distribution on the metal slab would account for this electric field? Well, if I see. Okay, so I'm not showing what I think I'm showing. Okay, so if I have my plates and remind me, which side was positive, left or right? Left?
Or to the right. The right.
Oh, this was a positive over here?
Yeah.
Okay, so I've got positive here and negative here. And this is connected to a battery. Now, without the slab, I have field lines that are going to go from the positive to the negative. They're born on positive charge and they die on negative charge. Now, if I put the slab in there, first of all, this is going to get to be a bigger sigma, and there's going to be a bigger sigma negative. But when I put that slab in there, well, that's just not a good. The slab has a 0 electric field in it. And I'm going to represent the metal with this cross hatching here. Well, I still got positive charges here. And they're going to give birth to field lines. And those field lines are going to go towards the negative. And they have to die on negative. And so for every positive charge I have on this plate on the right, I'm going to have a negative charge, the equal size, on the right-hand side of the slab of metal, okay? So that means I'm going to have a negative sigma on here. Now, those electrons had to come from somewhere. They came from over here. Every time an electron went to the right, it left a naked proton over on the left. And those now give birth to field lines that go and end on this side. And so these field lines continue. They just have a vacation in the metal where they don't exist. Now, if I can ask for your indulgence and patience with me being over pedantic, if this is 6 coulombs per meter squared, then on this surface here, I'm going to have -6 coulombs per meter squared. And on this surface here, I'm going to have +6 coulombs per meter squared. And here I'm going to have -6 coulombs per meter squared. Now that's bigger than what I had up here before I put the slab in there. Up here, I only had 4 coulombs per meter squared, and a -4 coulombs per meter squared. That's because when I put in the slab, because of that freebie section, I have to increase the electric field everywhere else, so that I have to do the same amount of work to get from negative plate to positive plate. The battery forces me to do the same amount of work as I go from the negative plate to the positive plate. Does that answer your question, Steve?
Yeah, thank you.
Okay. Yes, sir. JK. Practice exam 1. Help me out, JK. I just have 2 exams here and I don't remember which is which. You don't mean this one, right? No. Yeah, we did in class. So what you mean is the muon problem. Okay. Now, it turns out that the muon problem kind of psyched some of my students out. Because, hey, we never saw a muon, Greg. We were there in the class every day, and we never saw a muon. What's a muon? And it says right in the problem what a muon is. It's a fat electron, okay? It's got a mass that's roughly 200 times larger, so that it's 1.88 times 10 to the minus 28 kilograms. But it has the same negative charge that we have on an electron. So it's just like, you know, it's an electron, but heavy. Okay, so what we're doing is we're speeding it up from rest, and we want to get it to the speed of light, ignoring relativity, which we're going to have to, you know, touch on at the end of the semester. I wrote this problem because some goofballs at CERN announced that they had proven Einstein wrong. We just proved that he was full of beans. And it turns out that they were full of beans. They had just not done their calculation correctly. So I wrote this problem just to celebrate that fact. Einstein's theories really make some weird, outlandish predictions, you know, about time slowing down and lengths contracting that just don't seem reasonable. Until you start looking at the evidence. It turns out that, for me, the biggest evidence is that your GPS, you know, if you use a GPS machine, it takes into account Einstein's theory of relativity, and I'll explain that when we get towards the end of the semester. But you know, if you don't take into account Einstein's theory of relativity, that GPS is going to get you where you want to go, you know, give or take 16 kilometers, you know. But if you put in Einstein's theory of relativity, man, mine can get me right there where I want to be, and a military one can get you sitting on a dime. So that's not going to be on the exam. This is going to be just like those sample problems that we worked today in class. We start with the Verk energy equation, and because it's a particle that's very small, we only need to worry about these two buckets: kinetic energy and electric potential energy. And because we're just letting it go, we're not doing any Verk on it, that's zero. And so if how come I got something different over there than I got over here? Oh, I know. There we go. Is that more better? Okay. So that means that the change in kinetic energy has to be the same as the change in electric potential energy, but with a minus sign in front. And so this is always initial to final. And so we're going to have 1/2 times the mass of 1.88 times 10 to the minus 28 kilograms times the speed, which we want, which is 3 times 10 to the 8th meters per second, if you'll believe it, squared. And then we've got to subtract off the initial kinetic energy, but it starts from rest, so that's 0. And so that's going to equal, there's the minus sign that is the zero-sum game. One of the buckets is filling while the other one empties. And then we have the minus sign from the fact that it's got the same charge as an electron, negative 1.6 times 10 to the minus 19 coulombs. And then we've got this voltage from initial to final. That's what we're looking for, that right there. Well, you see that the left-hand side is positive, and the right-hand side, I got 2 negative signs which cancel each other out. So if I want the right-hand side to be positive, my change in voltage had better be positive. And we know that's the case for negatively charged particles. They speed up uphill, okay, as the voltage is getting bigger. So I expect a positive answer. But at this point, it's just math. I just plug into my calculator, calculator, and what I get, I don't want to drag you through all the punching of my calculator, but I get a voltage difference of 5.3 times 10 to the 7 volts. Now, you see, JK, that that's exactly the same as one of the practice problems we did in class today, except that we had the electron mass here instead of this muon mass. But other than that, it's exactly the same as what we did in that sample problem. Yes.
Are we gonna do a lot of like unit conversions, like micro and nano and?
Well, it's good to know micro and nano. I mean, those two. I mean, it's not like I'm asking you to memorize all 12 bones of the body. It's just those two. Okay. Micro is 10 to the minus 6. Nano is 10 to the minus 9. Okay.
Can we do homework 6, number 2?
Certainly. That's a very good choice. I commend your choice in problems. The reason I think that's a really good choice is because I have a feeling, and it's a strong feeling, that there's a problem similar to that on the exam. Okay, so and sometimes my feelings come true. Every single time. So we have this particle, and it has some mass, let's say 1 kilogram, and it has some charge. We're gonna take it to be 3 coulombs, and you get different numbers. Each student is given different numbers there. But we find that if we drop it onto a floor or towards a floor, that once it is dropped a distance of 5 meters, it's really, really humming. It's got a velocity. We'll call this point B and this point A. It's got a velocity at B that is 20 meters per second. Okay. Now, that's faster than it should be going. And the reason it's going faster is because this isn't any floor. This is a floor that's been painted with charged paint. Now, we have this Verk energy equation. And in this case, I have 3 buckets that I have to worry about. Because the mass of that ball is significant, the gravitational potential energy plays a part. But I just drop the ball. I don't do any Verk on the ball. I just drop it. So the Verk is 0. And that means that these 3 buckets have to add up to 0. Well, the change in kinetic energy is just going to be final minus initial. If I'm going from A to B, that's going to be the kinetic energy at B, that's final point, minus the kinetic energy at A, that's my initial. Well, it started from rest, so that's 0. And so it's just the kinetic energy at B, which is 1/2 times 1 kilogram times 20 meters per second squared. And that's going to be 200 joules. Now, the change in the change in gravitational energy is gonna be mg times the change in elevation. Well, that's gonna be 1 kilogram times 10 newtons for each kilogram, really 9.8, but we call it 10. And the change in elevation, it's going from 5 down to 0. That's a change of -5 meters. And maybe, I don't know, if this is 3 meters, it's actually going from 8 down to 3. The point is, the change is a -5. And so that's going to give me a change in this bucket of -50 joules. Now, if I drop something on a regular floor and it lost 50 joules of gravitational energy, it would speed up such that it increased its kinetic energy by 50 joules. It would just slosh from one bucket to the other. But that's not what happened here. I dropped this ball, and instead of speeding up with 50 joules of kinetic energy, suddenly it's got 200. And so something is going on here. And that something is that this floor is attracting that positive ball. So this floor must be painted with negative paint. Well, that tells me that there's an electric field in this region due to the floor that's towards the floor. Right? That's the formula for a single sheet. And so we're going to find out just how big that is, that segment. So let's go up here. My Verk is 0. My change in kinetic energy is a plus 200. My change in gravitational energy is a minus 50. And the change in electric potential energy, A to B, has to make up the difference. That has to balance the checkbook, as it were, okay? And so that tells me that the change in electric potential energy from A to B has to be negative 150 joules in order to make that balance. Well, I also know that the change in electric potential energy from A to B is equal to the test charge wondering whether people can see that at home. Maybe I should be using black ink. Okay. Times the change in voltage from A to B. Well, that means that negative 150 joules is equal to a positive 3 coulombs times the change in voltage from A to B. And that gives me the change in voltage from A to B is equal to negative 50 volts. So I don't know what the voltage is at A. I don't even care. But I know that the voltage at B is going to be 50 volts smaller. So if this is 600 volts, I made that up, this is going to be 550 volts. And as promised, the electric field turns out to be towards the floor, because the electric field goes from high voltage to low voltage. And if I want to know how big that electric field is, I use my ED equation. I know the direction of the electric field, so I'm just going to look for magnitudes. This is going to be E times the distance from A to B. And so if this is the magnitude here is 50, and I'm going to write that as 50 volts. And that's going to equal what I'm looking for times 5 meters. And that's going to give me an electric field strength of 50 volts divided by 5 meters is gonna be 10 volts per meter. And so now you see that I can find out what sigma is just by using the formula for the electric field in terms of sigma. Now, here's something to be aware of. If you know the voltage difference from A to B, you better be using the distance from A to B. And even if I ask it in a tricky way, like saying, well, what's the electric field at point A? Well, you don't want to be using this 8 meters from the plate. You need to use your head and say, well, that's just tricky talk, Greg. The electric field at A is the same as it is at B, it's the same as it is halfway between A and B, same as it is everywhere above the floor. And so I just need 2 points that I know the voltage difference between, and then I want to use that distance in my ed equation. Okay, always make sure that these indices are the same as those indices. That's your safety net that keeps you from making mistakes.
I have a question about when you, I mean, every time we've done this kind of equation, this kind of practice, the work has been 0. Is there ever like a time where the work won't be 0?
You know, there could be, if I said that a hand started it here and sped it up by pushing with a certain force up to there, then the work would be something other than 0. But you know, all the problems in the homework and all the problems on the exam, we just let that sucker go, you know, and
Sounds good.
yeah.
There's a technical problem where that happens in homework 7, because what happens is you let the ball go initially, but then it asks you to say, what's the word of the ball going to the other side? It kind of does that.
Oh,
There is a problem.
oh yeah, you're right. You're very, very right. In that problem, I actually did say, what if I did grab a proton and drag it from 3 to 2? How much Varric would I have to do? You're right, that's an example. Yeah. But at that point, you kind of figure that it's not 0, because I'm asking, how much Varric would you have to do to get it over there? Yeah. Thanks for reminding me. Yes, sir.
Did you go over question 7 in sample exam 1? Question 7, this guy. It's the one that talks about the 2 balls.
Oh, yes. You remember when we were talking about lightning rods? I set up a piece of metal that had a pointy end, and oh man, that's just not a good drawing. So I set up a piece of metal that had a pointy end. And we found that because the electric field inside the metal is 0, it cost me no Varric to take a test charge anywhere inside that metal. And what that meant was that the voltage difference is going to be 0 everywhere inside the metal. It's an equal voltage volume, because I can take a test charge anywhere inside there without doing any Varric. Now, if I change the shape a little bit so that I have a small metal ball connected by a wire to a big metal ball, because that wire connecting it is metal, again, it's an equal voltage volume. I'm gonna have the same voltage here relative to some reference point as I do there. It would cost me no VARIC to bring a test charge from here to there or from there to here. Now, in the case of this metal, we found out that because the field lines have to be perpendicular to the surface of the metal, the field lines are going to spread out near a point, whereas near a more flat surface, they're going to be more parallel. And because I have to do the same amount of VARIC to bring a test charge in this way as that way, that means I must have a very strong electric field here and a kind of mediocre electric field here. So here I'm fighting a mediocre field for a long distance to get it there. Here, I got no field, practically no field out here. I better really have to fight when I get close. And so that's why we said that all the charge was going to be, most of the charge is going to be concentrated right there on the surface near that point. Okay? Now, very little charge out here. Well, I can think of this as the point, and this is the kind of the less pointy end. And so I'm going to get a very high concentration of charge here and a small concentration of charge here. But your choices in this problem were the two spheres are at the same voltage. Ding, 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 ding. I know that's true. But I need to consider part B as well. The two spheres have the same charge. Well, it concentrates at the smaller radius, so that's not true. And the two spheres are producing the same electric field at their surfaces. We know that's not true because of what we found with the lightning rod. And so A is the right answer. Now, I have repented of that problem in the intervening years. And that is, as you can imagine, when this exam was given, that question didn't go well with the class. They really didn't have, we didn't spend enough time talking about the lightning rod that they felt comfortable with B. They weren't really sure whether B was true or false. And so in the end, I ended up giving them credit whether they said that A was the answer or whether they said that D was the answer. But since then, I've decided to mend my ways. So you wouldn't have a question like that. Yes, Miriam. Oh, as long as we're here. 2 point charges, Q1 and Q2, are placed on a line as shown. Where along the line would it be possible for an electric field of 0 magnitude? Now, we had a problem in the homework similar to this. And so let's remind ourselves what we did there. If we consider the three regions to the left of Q1, this would be part of answer A. Between would be answer B, and C would be to the right of Q2. Well, we know it can't be B because the contribution in here is going to be away from Q2 and towards Q1. And I can never add those vectors to get 0. And so it has to be either A or C. Now, the problem with A, I got them in opposite directions, so that's good. The E field due to the negative Q1 is going to be towards it, and the E field due to the positive Q2 is going to be away from it. But these two are never going to cancel each other because this E field due to the negative charge, I got twice as much charge here, and it's like 3 times closer. And so that contribution is always going to be much bigger. And so I can never make, this one's going to be so big compared to E2. But on the other hand, in region C, I can play off the fact that, oh, this one's closer. And so if they were both the same charge, this guy would dominate. But they're not the same charge. This one's twice as much charge. So maybe that's gonna dominate. And I can find a spot, just the right spot, where the closeness of Q2 is compensated for by the larger charge of Q1. So the answer is C. Yes. Long answer or long answer? Okay. On this same exam? This one here. Okay. Well, in this problem, we are told that the electric field due to the table that's been painted with charge at point A is going to be 50,000 newtons per coulomb up. Now, again, that's just tricky talk. The electric field due to a sheet of charge is going to be independent of distance from that sheet. And so that 50,000 newtons per coulomb up is going to be the field at A, it's also the field at D, it's the field at B, it's the field at C, it's the field over here. Going to be due to the table, going to be 50,000 newtons per coulomb up. Now, that means that this table is charged positively. I painted it with positive paint. Now, it turns out that the hardest question on this whole exam was the 205 review question. Okay. We remember that nature treats the vertical part of projectile motion differently than it treats the horizontal part. That as something flies through the air, if I just have gravity, then whatever I start with, let's say I've got 20 meters per second. Well, let's do the one that we've got in here, 15 meters per second. Okay. At 37 degrees. Well, because nature treats the horizontal part different than the vertical part, so do we. And so what we do is we break this up into an X part and a Y part. And you see that I haven't really drawn this at 37 degrees. 37 degrees would be more like that. So if I break that up into an X part and a Y part, the X part is going to be 15 times the cosine of 37 degrees. And that's going to give me 12 meters per second. And this is going to be 15 meters per second times the sine of 37 degrees. And that's going to give me 9 meters per second. Now, every second that ticks by, if this was noon when we fired it, at noon plus 1 second, if this was just a gravity problem, we would leave the X part, we would leave the X part alone. That would be 12 meters per second. And we would take the Y part and add 10 down. So instead of 9 up, I would have 1 down. And the total velocity would be something like this. Now, it turns out that because of that floor, we're going to get a different acceleration than 10 meters per second per second. It's going to be 13 point something meters per second, but it's still down, which means that the X part of the velocity is never affected whatsoever. Now, here's the key. That point A is at the top of the curve, at the top of the projectile. It's the location where the ball has stopped going up and started going down. And so right there at the top, all I've got is Vx. Vy's gone to 0. And so that's just going to be 12 meters per second. And it had nothing to do with electricity. It was just, let's see if they still remembered what they learned last semester. They didn't. Yeah, they didn't. Okay, so now let's go on to the electricity. Find the acceleration, magnitude, and direction of the ball at point A, which, by the way, is the same as at point B or point C, everywhere the same. Well, the first thing we want to do is draw a free body diagram. And what we've got on that diagram are two forces. We have a weight force, Earth on the ball. And I know how big that is. That's going to be the mass times G. And the mass we were told was 0.04 kilograms. G was 10 newtons for each kilogram. And we can assume G was 10 instead of 9.8. So that's going to be 0.4 newtons. Now, the charge of this ball is negative and the floor is positive. So that means the electric force is also going to be down. And the size of that electric force is given by Q test charge times E. And that's going to be 3 times 10 to the minus 6 coulombs times 50,000 newtons for each coulomb. And that's going to give me 0.15 newtons. Now, if I use F net equals MA, now let me just back up here. Why didn't I put a minus sign in front of that? I just want the magnitude. I know it's down. And so I just am looking for the magnitude. Okay. Now, if I wanted to be pedantic about that, I could have said, well, the force electric is going to be the test charge, which is negative 3 times 10 to the minus 6 coulombs times the E field, which is 50,000 newtons for each coulomb up. And that's going to give me a force of 0.15 newtons in a direction of negative up. And that's where the minus sign goes. Negative up is down. Okay, so if I add these two forces together, I have a net force of 0.55 newtons down and a mass of 0.04 kilograms. And now I just solve for A, and this is 0.55 newtons down, so my acceleration is going to be down, and it turns out that that's 13.75 meters per second squared down. Okay. When the ball is at point A, we want to find the total electric field at point D due to both the ping pong ball and the sheet of charge. Well, the electric field due to the sheet of charge was easy. That's just going to be, we're given that's 50,000 Newton per Coulomb. So now we just need to find the E field due to the ping pong ball. Well, because we're told that's concentrated in a uniform sphere, we can treat that as a point charge. And I drew that up because it's a negative charge. And so the E field at D would be towards A, where the negative source is, up. And I can find that field just by taking K times Q source over R squared. K is going to be 9 times 10 to the 9th. The Q source absolute value is going to be 3 times 10 to the minus 6. And the distance is going to be between A and D is going to be 1.5 meters, and I'm going to square that. And when I do that, I get 12,000 newtons per coulomb. Well, now the E total is just going to be the E due to the sheet plus the E due to the ball. And that's going to be 50,000 newtons per coulomb plus 12,000 newtons per coulomb, or 62,000 newtons per coulomb. Now, the hardest part of this problem was part D, where we're asked to find the voltage difference between point B and point C. And here we have to be creative. We have to use the fact that the voltage difference from one point to another point is completely independent of path. And I don't like that curve path. If I'm going to do that curve path, I'm going to do some pretty fancy calculus. And I don't want to do that. That's just not right. So I'm going to pick a path that I like. And that path is I'm going to choose a point Z that's also a ½ meter above the sheet, but directly below, let's see, directly below B. I'm going to call that Z. And then what I'm going to do is I'm going to say the change in voltage from B to C is equal to the change in voltage from B to Z plus the change in voltage from Z to C. Now, the thing that's flying from B to C is my test charge, okay? And the change in voltage doesn't depend on the test charge. It just depends on what's pushing on the test charge. And so what I need to consider is only this field due to the table, which is up. And so that means that if I move from Z to C, which is perpendicular to that field, that's an equipotential surface. There's no change in voltage along that line. And so I can say that this is 0. So all I need to know is how much does the voltage change in going from B to Z? Well, I'm going to B to Z, I'm pushing against, remember voltage is reaching into your pocket, pulling out 1 coulomb. How much Verc would I have to do if I pushed it from B to Z? Okay, well, that path from B to Z is opposite the field. Okay, so I'd have to push in the same direction that it's going. So I'd have to do positive Verc. And the Verc that I would have to do would be given by the Ed equation. I would say that the change in voltage from B to C is just equal to the change in, change in voltage from B to Z, which is just going to be 50,000 volts per meter, I'll write it as, times the distance of 1.5 meters. And that's going to give me 75,000 volts. And it'd be a positive 75,000 volts. I'd have to do positive Verc to get it along that path. Now, the last part, what's the surface charge density? Well, 50,000 newtons per coulomb is equal to sigma over 2 epsilon naught. And so all I got to do is solve that for sigma, 2 epsilon naught times 50,000. And that gives me a number that we can punch into our calculator. Yes.
On part B, would you elaborate a little more on, so we know the ball is negatively charged, and we know the field is positive. So could you explain how we're bringing positive there down?
If we were to take that ball and push it down to Z, we'd be doing negative error. But that's not what voltage is. Voltage has the waffle words in it. Voltage is the rate, how much you pay for a gallon of gas. And that's always moving plus 1 coulomb. When you're dealing with voltage, you're always reaching into your pocket and you're always pulling out that same plus 1 coulomb. And if I know how much Verc I have to do for a plus 1, then I can figure out how much I have to do for a minus 3 times 10 to the minus 6. What I would do is I would say the change, oops, I don't want that one. Black shows up better. The change in electric potential energy from B to Z is going to be the change in voltage from B to Z, but it's scaled by what I actually move from B to Z, the test charge. And so that's going to be a negative 3 times 10 to the minus 6 coulombs times 75,000 volts, which is a volt is just a joule for each coulomb. And so you see, I'm going to get a negative change in my electric potential energy, meaning that bucket's draining, which means my charge is speeding up. Okay.
the ball itself and the floor. If you then use the 62,000. It's for kilometers.
The,
That's not.
the change in voltage from,
Instead of going from 2 point from E to C.
oh, okay, if I wanted to know the change in voltage, from point A to D, I would, take, in that case, it'd be exactly the same change in voltage, 75,000 volts, because I got the same E field that I'm fighting and the same distance of 1.5 meters. Yeah. So that would be the same. Greg?
Could you re-explain why that change in voltage was the sign that it was? That it was positive rather than negative?
The 75,000?
Yeah, could you just explain that?
Oh, okay, so. If the electric field due to the sheet is up. Then if I had a +1 coulomb, it would feel a force up. And that's what the electric field tells me, is how much force would it feel up? This is 50,000 newtons for each 1 coulomb. So that means that this electrical force on 1 coulomb would be 50,000 newtons up. Well, if I want to push this so that it moves at a slow, constant speed, fighting that field, I'm going to have to push with the hand. And that's the external force by the hand. And that's got to also be 50,000 newtons. And since I'm pushing down and it's moving down, those two are in the same direction. That's positive air. Whenever I'm pushing in the same direction it's going, that's positive air. Okay, our time is up. If you have questions tomorrow, I'll be in my office. Just stop on by. And you have my phone number. So you have resources.
Thank you, Dr. Francis.
Thank you.
Thank you.
That's right.